It'll be on your quiz, remember what we talked about last week, and then what we're doing this week, and then your quiz is on Friday. So keep that in mind. That also means your Delta Math 1 is due then as well. So when I'm factoring, what should we always look for to factor first, everybody? Yes, what's our GCF number 1? And everybody, if you ever have a two-term that you're trying to factor with a minus in between, remember what you should look for is difference of squares or difference of cubes. So what did you notice about both of these terms? They're both cubes, so is this how I factor that? X minus 4, I take the cube root of all of that and then I throw a cube on the outside? No, I do have my first factor of x minus 4. Remember, I do not just kind of put that cube on the outside and call that a day. That would not equal the same thing, because you would have x minus 4 3 times, and that's not going to give you back x cubed minus 64. What will, though? What would my second factor be here using that sum and difference of cubes formula?
Squared plus 4x plus 16.
Good job. X squared plus 4x plus 16. So remember, it's your first term, all squared, opposite sign, multiply for your middle, and then last is this term squared, which is 16. What about with question 2? Once again, two terms. Were these perfect squares or perfect cubes? Squares. So my factors would look like x squared minus 1 and x squared plus 1, and is that it? We're done here? No, what could we still keep factoring?
X squared minus 1.
Great job. So that would become what? What would x squared minus 1 factor into?
X squared minus 1.
Can I keep factoring x squared plus 1? No. So remember, if you see a plus, you can't keep factoring. It's only if it's a minus with perfect squares. With cubes, you can keep factoring if that was a plus, but not if it's a minus. What other questions do you guys have here? All right, so like I said, lots of stuff to get into today, lots of like vocabulary. So today's gonna definitely be like heavy note taking. So for those of you that I know some of you guys like to do your work on whiteboards, it's lots of vocabulary today. So if you need a space to like write things down to remember to refer back to later, go ahead and take that out as we start moving to class. So let's talk about where we've been and then kind of like what we're getting into today. Where we've been is we've graphed things that look like this before, right? We've done this back in algebra 1, like y equals 3. You've graphed a linear equation time and time again, like y equals 2x plus 5. And then this year we've graphed quadratics. So this side on the left is where we've been before. In a lot of these, you'll notice how like n equals next to it, and the n equals is describing the degree. Can someone remind us from last week, what does the word degree mean? Exponent, like so you're my highest exponent, right? So the quadratic, my highest exponent was 2, so my degree is 2. And this might be more of where we're headed, what we are kind of working on in our polynomial unit. Right on the right side, we have a cubic function, a quartic function with my degree of 4, quintic with my degree of 5. I want you guys to take a moment, look on like the right side, maybe you can look back on the left too, and I want you to talk with people at your table about just general characteristics maybe you're noticing or connections you're making to these graphs. So there's no right or wrong answers, it's just really kind of like about what you're noticing. So hopefully you guys will notice some good ideas that'll help us into some vocabulary for today. So go ahead and get started talking with people at your table, like what are you noticing with these graphs? Alright, let's see what you guys are thinking. So, we're gonna go table by table. I'm just gonna share a thought that you have made looking at the graph. So, like I said, there's no right or wrong answers. It's just kind of like, what do you see? What do you notice? So, what did you guys, this first table here near my desk, what did you notice?
When it says n equals, it's talking about the highest exponential value.
Oh, the highest exponent? Good. So, remember your highest exponent, what does that mean? It's your highest exponent means degree. Okay, good. So, notice in each your degree. Is that highest exponent? Good. That was something we kind of just discussed earlier. Let's hear from you guys in that back corner table. What other ideas did you see? Nice, Laura. So, when my degree is even, so connect back with our quadratic, right? They're going the same direction. You were talking about like the ends of the graph? Nice. So notice both of these ends are going down. My n is 4. They're both going up. But when my degree was odd, they were going in opposite directions. Opposite directions here with 3 and 5. So I'm going to jot down these nice ideas. So, degree is highest exponent. And then we have the idea of end behavior. Even degree. They'll go in the same direction. Opposite degree. Or sorry, I should say odd degree, they'll go in opposite direction. Alright, what about you guys on the middle back table? What other ideas do you have?
After like n equals 2, each increase of n, it's like it adds another curve.
Ooh, another curve. So, what did you call this, like, kind of curvy point back in a quadratic? What did you call that? The vertex. So, how many, quotation marks, vertexes did cubic have? 2, and what about quartic? 3, and then what about this quintic? Okay, good. So this, vertex that you were used to back in a quadratic is a new vocabulary idea which we call a turning point. So those turning points occur on your graph, and notice the amount is going to increase with your degree. So your turning point is kind of like a vertex with your quadratic. What about you guys in that front middle table? What else did you see and notice? You guys notice anything we haven't said yet?
With the degree then you have 5 different angle lines. So one is just two separate lines.
Oh, like 2 places of I see what you're saying, right? Like with 2, it's like increasing and then decreasing, with 1 it's increasing the whole way. Nice, so that's going to connect back with your turning points. So kind of what Arch is getting at with that, and what your turning point does, it's going to be where you change direction, right? Like if you're driving and you have to make a turn, you're changing your direction. So it's where you change direction, meaning what's happening here with your quadratic? What are you doing until your turning point? It's increasing, yeah, kind of like that pot going up. And then what are you doing after your turning point? Decreasing. So it's going to be where you're changing or increasing and decreasing. Nice idea to expand on that. What about you guys? What else did you notice? Besides, they look like the heartbeat machines. Anything else? Do you have anything else you kind of noticed? What about you guys, that back table near the door? Did you have anything different that you noticed that we haven't said yet? Any other ideas? No? What about, before we kind of move on, any other ideas that maybe you talked about with your table, or any other ideas you guys are noticing at all before we start expanding on these even more? This is a good start. We're going to, like I said, expand on these more. We're going to expand on these, like that degree, and what the degree can really do for us. We're going to expand on end behavior and how I can really predict end behavior looking at just an equation. And we're going to expand on your turning points and how you can predict the amount of turning points you'll have looking at your degree. So let's get into it. This was just kind of to get our ideas thinking. So let's start talking more about our vocabulary. And our first idea is the fundamental theorem of algebra. If that doesn't sound important, I don't know what does. So this idea talks about your degree. Who can remind us, what does the word degree mean again? Your highest exponent. So your highest exponent of a polynomial is going to determine how many roots it has. What does that word roots mean? Yes, roots means solutions. Roots means your solutions. How might you look and see your solutions if you're looking at a graph? Where can you find solutions? If you have a graph, where do you find your solutions? Yeah, where are they specifically? What points are they? The intercept on what axis? Yes. So they're your solutions. They're your x-intercepts. Meaning, when they're on your x-intercept, those are your what type of solutions? Those are your real solutions. So if they're on your x-intercept, that's when they are real solutions or real roots. If I had a quadratic, right, and I saw it cross the x-axis 2 times, I would have 2 real solutions. What if I never saw that quadratic cross the x-intercept? Those were imaginary types of solutions. So your degree determines how many roots it has. So types of roots that you're going to get into today is you could even include multiple repeated roots or non-real imaginary roots as well. So let's look at this example here. We have x to the 4th minus 7x squared plus 3. What is the degree of this function? Yeah, it's 4. It's a quartic. That's a nice connection. So here's my highest degree term. My highest exponent is 4, so the degree is 4. So if my degree is 4, what do I know? How many solutions or roots will I have? 4. So this means 4 roots. So let's talk about the possibilities we can have from here. I have 4 roots, meaning I could have 4 real roots, right? That would mean my graph would cross the x-axis how many times? 4. So let's look back at this picture here with my quartic. Look, I crossed my x-axis 1, 2, 3, 4 times. So that would be an example of what something would look like. So I can have 4 real roots. I have other scenarios of other types of solutions I can have. And my other types of solutions could have imaginary solutions as well. So let's think back to our work with our quadratics, right? You can have 2 real solutions. You could touch your graph 2 times. Or you could have 2 imaginary solutions, because my degree there was 2. So where did my 2 imaginary solutions come from? Think about when you were solving your quadratic, right? You look to see if you could factor at first. What would you do to solve if you couldn't factor? Your quadratic formula. And how would you recognize in your quadratic formula that you had an imaginary solution?
Negative discriminant.
Negative discriminant, good vocab there. So underneath my square root here became negative. What's in front of my square root with my quadratic formula? Plus or minus. So with this plus or minus, your imaginary solutions are always going to come in pairs because they're going to occur when I get down and I have a quadratic and this is negative. So my imaginary solutions are going to come in pairs from my quadratic formula with this plus or minus. So if my imaginary solutions have to come in pairs, what are the other solution types I could potentially have? If I can have up to 4 solutions. What's another solution type we could have?
Repeated.
What was that?
Repeated solution.
Not quite. We'll get there in a second. We can kind of hold off on that part for now. Just talking about your imaginaries, right? If I can have up to, so this is like a game of points. Think about if I have a degree of 4, that means I should have 4 solutions. So, what are my other possible solution types? No, just think about just imaginary, right? So maybe let's just focus on imaginary solutions. Could I have only one imaginary solution? What did we just talk about? Imaginary solutions have to come in
Pairs.
pairs. Okay, pairs means how many? 2. So could I have 2 imaginary solutions? Yes, if I have 2 imaginary solutions, think about what's left over. How many? 2. So those 2 other would have to be real. Good. So I could also have 2 imaginary and 2 real. What's my other possible scenario? All imaginary. Think about they have to come in pairs. So meaning I have 2 pairs, that's going to give me 4 solution types. So kind of think about your degree. No, option 1 is all real. After that, you can kind of break it down into groups of 2 to see how many imaginary solutions you would have. So let's look at our next example here. What's our degree? 5. My highest exponent here is 5. So degree is 5. That means we should have how many roots? 5 roots. So what are my possible solutions here? What's one possibility? 5 real roots. Kind of think about it's a game of points. So I have 5 total that I have to always add up to. So these are all 5 real, so that's one option. What's another option?
3 real and 2 imaginary.
Good job. So kind of think go down by 2, right? So that would mean this is one imaginary pair of 2, and there's 3 left over for my real. So we get 2 imaginary and 3 real. What's another scenario we could have?
4 imaginary, 1 real.
Great job. 4 imaginary and 1 real. What would that look like graphically? How many times would you cross the x-axis?
Once.
Once, right? 1 real means I cross the x-axis 1 time. Could I have any other scenarios? Can I have 5 imaginary? Why not? It has to have a pair. Think about if you were to create a group of 5. Would you have perfect pairs with the 5?
No.
Nope. So, key takeaways with your fundamental theorem of algebra. Degree means that's the amount of solutions you're going to have. Imaginary solutions come in pairs. What other questions do you guys have here?
Can you have 4 real, 1 imaginary?
No, because 1 imaginary Do you have a pair? With just one?
Then how come you can have 4 imaginary?
Because 4 imaginary means groups of 2. And then 1 real.
Oh, so real doesn't need a group.
Awesome. Good connection here that I was just making. Does real need a pair? No. So reals does not need a pair, only imaginary, because of that plus or minus with your quadratic formula. What other questions do you guys have? Alright, so things we just talked about a little bit. Your real roots, who can describe? I know a solution is real because where do I see it on the graph? Good job, it's crossing the x-axis. Am I going to see an imaginary root when I'm looking at a graph? You're not going to see it. You only see your real ones, right? Because that's where it's really crossing the x-axis. Those are my real roots. But my imaginary roots are going to come in those conjugate pairs, meaning you should always have groups of 2 with imaginary roots. So think about groups of 2. Multiplicity is a new idea we're going to talk about as well with my solution types. If you see multiplicity, that's our vocabulary word. What maybe stands out about that word multiplicity? Maybe multiply or multiple. So multiplicity means this root is going to be a root multiple times. So that just means this one root is happening multiple times. And we're going to deal with either a multiplicity of 2 or 3. And we're going to see what those look like on the graphs next. Alright, so let's look at our multiplicity here. Let's start off with things that we know, looking at a quadratic. I know looking at this quadratic here, I have 2 real solutions. How do I know I have 2 real solutions? Crosses the x-axis 2 times, so what are my 2 solutions? Great job. X equals 0, x equals 2. I also know this scenario all the way over here on the right side as well. I have 0 real solutions. How do I know I have 0 real solutions here? Great job. It never crosses the x-axis. So I know it's a quadratic based off of that shape. So I know, therefore, I have to have 2 solutions. And if I don't see it cross the x-axis, that means those 2 solutions are imaginary. Now let's talk about this next idea. Looking at this quadratic here, notice the vertex is on your x-axis. So how many times do I touch the x-axis? Once. So what was my solution here? 1. So this is where we were before. We would just write my solution as x equals 1. But we're building off of this today because based off my fundamental theorem of algebra, if I have a quadratic, I know I should have how many solutions? 2. Degree of a quadratic is 2. So therefore, how many solutions do I see right now though? 1. So what does this mean? This means x equals 1 has a multiplicity of 2. Basically, how I like to describe this is what's going on at the x-axis is a bounce. Because this is a quadratic, right? I'm approaching x equals 1. Basically, I'm like boom, boom, and I hit x equals 1 2 times really fast right here on that graph. So because that's a if you look like a quadratic touching the x-axis, think about quadratic degree 2. That's it, kind of touching 2 times right there on the x-axis for you. So what would that look like and kind of why does that happen? Is because if I'm crossing my, or touching the x-axis at 1, what was the factor that goes here? Great job. So x minus 1, but remember it's a quadratic, so kind of think about what does that look like? It's x minus 1 squared. So basically this exponent of 2 means x minus 1 happens 2 times when you're solving. That's why that's happening. So basically now, if you see it touch the x-axis, you can't just only write x equals 1. You have to talk about the multiplicity on top of that as well. So let's talk about that third situation, which is having a multiplicity of 3. So multiplicity of 3, why multiplicity of 3? What function type does this look like right here on the x-axis? A cubic. A cubic has a degree of what? 3. So maybe you are describe it as a cubic function touching the x-axis, or I like to maybe say it's having a wiggle through the x-axis. You know, it's got that wiggle right through the x-axis. It's a cubic function. That's kind of what it looks like, right? So right here, I'm touching the x-axis at what point? What point does this function touch the x-axis at? 0. So I would have x equals 0 with a multiplicity of how many? Multiplicity of 3. So it's that cubic function with that wiggle. Because what does this equation look like? It looks like x cubed equals 0. Meaning I have x equals 0, x equals 0, x equals 0 3 times. That's getting me up to my 3 for my solutions for my degree. So now when you're looking at your real functions, you're not going to just be noticing where it's crossing the x-axis, but you're going to also be noticing kind of how many times does it cross the x-axis. And obviously, if you go straight on through, like with our first example, that's just a multiplicity of 1, because you're just passing right on through clearly. But remember, vertex, bouncing, multiplicity of 2, cubic function, got that wiggle through, multiplicity of 3. What other questions do you guys have here? All right, let's look at some more vocab. And let's talk about those points you guys were talking about earlier in class today, which are turning points. Remember, we described turning points as where you're turning, right? You're changing direction. And you guys noticed you were changing from increasing to decreasing or decreasing to increasing. So that's our definition behind a turning point. They're super important when it gets to calculus. Kind of where is that graph changing, right? Why are we changing from increasing to decreasing and decreasing to increasing at these points? So another important idea is noticing the connection between degree and turning points. So I want to look back at the beginning slide. And what did you guys notice between turning points and degree here? Anybody see a connection?
Turning points, the amount of turning points is equal to degree minus 1.
Great job, Liam. So noticing here's my quadratic. I had 1 turning point, my degree is 2. Here's my cubic, I had 2 turning points, my degree is 3. Quartic, I have 3. So let's put that into our thoughts, ideas. You know your turning points. Your degree will be equal to the amount of turning points you have minus 1. Oh, sorry, other way around. Your turning points will be equal to your degree minus 1. So remember with my quadratic, my degree is 2. Remember you always have 1 vertex point or 1 turning point. So let's look at the difference between these two graphs to kind of see What else are you noticing about turning points? So we have two graphs here. What are you noticing about these two? What's something that you notice they both have? Great job. They both have a degree of 3. So now let's look at them individually. And if you're looking at this first one, x cubed plus 2x squared minus 1, what are you noticing about this graph here? Has a degree of 3. What else do you see about this graph?
3 real solutions.
Ooh, good connection to what we were just talking about, right? We have 3 real solutions. We touched the x-axis 3 times. What else do you guys notice? Good job, Liam. We have 2 turning points, right? Like here and here. Now let's look at our second example here. We have x cubed minus 1. What do you notice about this graph here? We only have 1 real solution. Just remember, that's going to come from, if you were to think about the factors for this, you'd have x minus 1 and then x squared plus x plus 1. Remember, it's your difference of cubes. So your 1 real solution comes from this linear factor here of x minus 1, which makes sense of why we have a real solution at positive 1. And this part's imaginary. So 2 imaginary, 1 real for my degree of 3 here. What else do you see? What else do you see when you look at the graph? I know it kind of might seem like that, but if you zoom in and follow along with your finger, what do you notice this graph is doing the whole time? It stays increasing. So if I stay increasing, do I ever turn or change directions? No. So will I have 2 turning points? No. So this turning point rule does not mean it will for sure have that many turning points. It means it can have up to that many. So in this example here, we had 2 turning points, right? My degree minus 1. That's how I got 2. 3 minus 1 gave us 2. My second example, I had no turning points, and that's okay. Just notice I still had the shape of my cubic function. This rule just means I can have up to that many turning points. That's the maximum you can have, but you can have less than that as well. What other questions do you guys have here? All right, now last big vocabulary idea is our end behavior. So Laura was created, that table back there, created some nice ideas and examples when we looked at those graphs earlier. Noticing that the ends of the graph will go in the same direction if you're even degree, and if you had an odd degree, they'd go in opposite directions. So if my n is even, meaning my degree, let's start there. My degree is even. This a means your coefficient. So really can we connect back to your ideas of a quadratic and what those graphs look like. If my a is positive, meaning if I was graphing something like 5x squared, my degree is even, my a is the coefficient in front, and that's positive. What would the ends of my graphs, or what would the shape of my graph look like? Would I look like a U or upside down U? A U, right? This is my quadratic. So my ends go in the same direction, meaning if I have a positive degree, a positive coefficient and an even degree, both my ends go up and up. Kind of what's happening in the middle, how many times my graph turns about is just dependent on the degree, but anytime my degree is even, they both go up and up. So my end behavior would look like as x approaches negative infinity, what would f of x approach? Infinity. What about as x approaches infinity, what would f of x approach? Great job. So thinking with both of those, both my ends are going up and up, so both my ends are approaching positive infinity. What about when my degree is even? So still think about a quadratic, but my a value is negative. What transformation happens when my a value is negative? It flips over the x-axis. So now my u is upside down u. So where are both my ends going?
Down.
Both going down. So think about this looks like an upside down u. So both the ends of my graph are going down, which means with my end behavior, as x approaches negative infinity, what would f of x approach? What do you guys think? I would approach where for both of my end behaviors? Good. Both going down, meaning negative infinity. What about when my n is odd? So my degree is odd. The table in that back corner with the flag, near the flag, told us they're going to be going opposite directions. So kind of think back to your linear function is what they're going to connect back to. So with that, with my a being positive, that's the coefficient in front of my x. What do I call that coefficient in front of my x if I'm graphing a line? It's the coefficient in front of your x. It is your slope. So thinking about positive slope. So this is going to connect to a positive slope, right? What does a positive slope look like? Something like this. So my ends on the left are going to go down, and my end on the right is going to go up. Kind of think about what's going on in between here. It's going to look different for each function, but what's on the end should look the same. So what's my end behavior? As x approaches negative infinity, where will f of x go? Negative infinity on the left here. Yeah, and what about as f of x approaches positive infinity, where will f of x go? Good, so think about with this one here, if it's odd and positive, these match up, negative, negative, positive, positive. And it can really be helpful too if you're not quite sure if you're going to have a positive or negative degree, and you have something like this. Put your pencil ends on the corners of your arrows and just think, okay, was this a positive or a negative slope? And if this is positive slope, my a value should be positive. And you see your arrows are going opposite ways, so your degree is odd. Now, last case scenario is your a is negative, and Morgan told us earlier that means slope. So slope is negative, so think about a line like this. My slope is negative, so my ends are going to kind of be the same as those ends, meaning on the left, this arrow would go up, and on the right, this arrow would go down. So what's in between here could be different. So what does that mean for my end behavior? As x approaches negative infinity, where would f of x go? As x approaches negative infinity, so on the left side, where are we going? Positive infinity, so you're going up. And as x approaches positive infinity, where's f of x going here? Good. And I have a little graphic organizer over here that helps you connect back to with your end behavior. And give you guys a couple seconds to finish jotting down any ideas, and then we'll work on some examples. Gavin? Yeah, just a minute, you hold fast. What was something you noticed from the beginning about this function? What did you see, Yana? How did you notice the degree was 4?
That's the highest exponent.
Awesome. Highest exponent it has. Don't get caught up in always thinking it's the first term. But so if it is the first term, that means, are we in standard form? Yeah. So y'all just told us our degree is 4. So if I know my degree is 4, what type of function is this? What do you call a function if the degree is 4? Quartic, good job. What else are you get all of your information really from this highest degree term. So what's the sign here? It is negative. And if my degree is 4, what's the maximum number of turning points we can have?
3.
3. My degree is 4. What are the number of roots we'll have? 4. Remember we talked about those possible scenarios earlier. All real, 2 imaginary, 2 real, or 4 imaginary. Now my end behavior. As x approaches negative infinity, what would f of x do? So I can find out my end behavior information from 2 places, my degree and my sign. My degree is 4. What do I know? Is that even or odd? I know 4 is even. Good. So if I have an even degree, my end's going to be going the same direction or opposite directions? The same. And if my sign is negative, are they both up or both down? Down. So I know my end's going to look like this and this. So as x goes to negative infinity, so look to my left arrow, I'll be going where? Down, which means negative infinity. As x approaches positive infinity, look to the right arrow, and I'll be going down as well, which means negative infinity. So that term gives you all your info. What questions do you guys have here? All right, let's try it again with another example. So I'll give you guys 2 minutes, jot it down, see what you're noticing, and then we'll run through it. You guys are thinking, what did you guys notice first about this function 4x squared plus 2x cubed minus 2? What's something you saw about this? Is it a quadratic? No. What's the highest degree? 3. The highest exponent means degree, so this is that term that's really important for me to look at. So my degree here is 3, which means we have what type of function then? Cubic. Alright. What else do you guys see? What's the sign of this? So this is still my leading coefficient. Because Morgan was asking this question, I don't know if everybody heard her. But like she was saying, do I have to put it in standard form? Like, no, you don't have to, but what you need to know is the sign of your leading coefficient should be like, what is the sign if you are in standard form? So if you are in standard form, this would go first. And what is this? Is this positive or negative? Positive. If my degree is 3, what's my maximum number of turning points? 2. I don't have to have 2, but I can have up to 2. And if my degree is 3, what's my number of roots? 3. I can have 3 roots. Meaning, what are my options with 3 roots? What's one solution type I could have?
3 real.
I could have all 3 reals, and then how many imaginary could I have? 2 imaginary and then 1 real. Now let's talk about end behavior. So if I'm a cubic function, so I'm going to go degree of 3, is that even or odd? We know it's odd. Does that mean I'm going to go opposite or the same? Opposite. And if my sign is positive, kind of think about, if you're not quite sure what it's going to look like, think about it's going to look like a positive sloping line. So if you like connect with your pencil here. So let's talk about end behavior. As x approaches negative infinity, what would f of x approach? Negative infinity. And as x approaches positive infinity, what would f of x approach? Great job. Those should match up. Meaning negative, negative, positive, positive. Alright guys, so you have looked at an example looking at the function type. Let's look now at our graphs. Any other questions here? So with graphs, we're going to have a lot more things we can look at, right? Because we're going to be able to see so much more. So let's see what we can find looking at some graphs. So I'll give you guys about 2 minutes. Jot down your question and see what all you can answer in these next 2 minutes looking at this graph. All right. What is one thing you noticed looking at this graph at first? So maybe one thing that just kind of stood out at the beginning.
3 turning points.
3 turning points. That's a good thing to notice. Here we have them. 1, 2, and 3 turning points. What else did you guys see from the beginning? How'd you notice the degrees for? Good job. We have 3 turning points. So if I have a degree of 4, what type of function do we have? A quartic. How else? What else do I know about my function? Good. How'd you notice the sign was positive?
The infinity lines go up.
Awesome. Both my ends are going up and up to positive infinity. So if my degree is 4, what's my total number of roots I should have? 4. So let's talk about what are my types of roots that I have. How many real roots do you see? Or where should I find my real roots, I should say? On the x-axis, how many points do you see on your x-axis? 3, right? But how many do I have to have an equal, though? Yeah, because would it make sense to have 3 real and no imaginary? That's only a degree of 3. So this is really 4 real solutions. And how do I know it's 4 real solutions? What else do you see on your x-axis?
At the bottom of the first turning point, it only touches the x-axis and doesn't go down.
Yes. So what you're saying at the first turning point, that turning point is touching the x-axis. Where is that on your x-axis? So what's happening when x equals -2 if you have a turning point right there on the x-axis? It hits it 2 times. We call that a bounce. That's your multiplicity. So this, if you're thinking about this in terms of points, right, you have to equal your degree, which is 4. So this means x equals 2 is like worth like 2 points because it has a multiplicity of how many? What does this have a multiplicity of? -2 is a multiplicity of how many if there's a bounce right there?
2.
2. Is that my only root? What else? What else do I have? What else do we have as a root? X equals -1. Does that have a multiplicity? No. What else does x equal? 1. So this is where I get my 4 points for my 4 real roots, my 4 solutions from. -2, think about multiplicity, 2 points, then 1, 2, more, 4, 4. What's our domain here? What do you guys see? What's our domain of our function? Good job, -infinity to infinity. What about our range? Think about bottom to top. What's the range? What do you see, Alda?
-5.
Yeah, it's -4.8. And then we'll use a bracket, so -4.8 to infinity. And where are we increasing? Where's the first point you're increasing when you go left to right? What do you guys see? What is- Oh, here to here? Yeah, let's go left to right. So where's the first point? First is here. -2 to, you want to call it -1.5? then we increase again, you said from 0.366 to infinity. And then where are we decreasing? Where do we first decrease? Good job. Negative infinity to 2. Negative 2. And where else do we decrease?
-1
Negative like 1.5
to, or yeah,
until
0.3.
good. Negative 1.5 to 0.366. And then lastly, our end behavior. I know my sign's positive, my degree's 4. Both my end behaviors are going up until when? Both are going up to infinity. Ba-boom, ba-boom. What questions do you guys have here? Yeah, Morgan?
You know how you said like the number of turning points is up to 1 lower than the total roots?
Uh-huh.
How come you can just assume that once you find, like, you know, you said turning points negative, you just assume the degree's 4?
That is a great question. So you want to look at both your solutions and your turning points in determining your degree. So if I saw 3 turning points, I could be like, I could have a good prediction that I was going to have a degree of 4. I should know for sure when I look at the x-axis to find my solution. So looking at my x-axis, I'm like, okay, 1 solution, 2 solution, boom, boom. That was 2. That was like a 2-pointer. So that was like, okay, I had 4 real solutions there. So therefore, I know that degree has to be 4 as well.
Okay.
So you should kind of look at both at the same time. Good question. Anything else? I forgot to mention that. All right, let's do one more. And then I'll start you guys on your classwork. And let's see what you were thinking. So what's something you noticed here first looking at this graph?
Degrees 3.
How did you notice the degree was 3?
2 turning points.
Awesome. We have 2 turning points. Our degree is 3. What type of function is this? Cubic. And what's the sign of our leading coefficient? Yes, it is negative, and if you're not quite sure how we find negative, remember it's going to connect back to a line. So put your pencil like on the end here, and think about what's the slope of this. This is positive or negative, so that's negative. What do you notice about your total number of roots? My degree is 3, so we need to have how many roots? 3. And then how many real versus imaginaries do we have? What do you see, Mithra? Good job. How did you notice that? Great job. So 1 is on the x-axis, so that means I'm really just finding one of those roots that I can see for sure. Where's that one root? X equals 3. Do I have a multiplicity? No. What's the domain of this function? Good job. And what about the range? Negative infinity to infinity as well. What about where are we increasing? From where to where?
0.184 to 1.8.
1.8. And where are we decreasing?
1.8 to infinity. Or
Yes.
from-
We'll start off with negative infinity, right? And then we'll go to 0.18. And then we'll unit because we have to keep doing more, and it'll be from 1.8 and to infinity as well. Then lastly, our end behavior. As x approaches negative infinity, where are we going? So on the left side, where are we going? Positive, so positive infinity. As x approaches positive infinity, where are we going?
Negative infinity.
Great job. What questions do you guys have here? All right, so that was our last example together for today. I'm going to hand out the classwork for you guys. You have like 15 or so minutes to get started on this classwork. So with